I have another problem for you to solve. This is a weird way of asking that. Anyway, my question is, which algorithm is better? Because that should be obvious. And why? And so imagine you're trying to come up with an answer that really just demonstrates your knowledge in a really crisp way. Okay, so think of an answer in English. All right. So I'd say, well, dupe 2 is clearly the better choice. One reason is it takes fewer operations to do the same job. So in this case, if we're using dupe 1, it takes 50,015,001 less thans compared to only 10,000 for dupe 2. That seems pretty good. I'd say a better answer is, well, the algorithm scales better. This n squared plus 3n plus 2 over 2, that seems worse than just n, right? It's more general. But I'd say an even better answer, maybe a little vaguer, but I think this is really what it boils down to. The most important point here is that parabolas, n squared, or quadratics, they grow faster than lines. And that's what we mean by scale. So these are basically the same answer, but I think really just focusing on the geometric intuition will really help us here. And in fact, I'll make a note here that geometric intuitions are useful in all kinds of domains. They pop up in computer science a lot. And I think that when it comes to data structures and algorithms, having this geometric picture is an important one here. So let's talk first about why we even care about scaling. So in most cases, I want to note we only care about the asymptotic behavior when n becomes very, very large. So if you start up, say, a social network, for your first so many users you have, it doesn't really matter what data structure you use. When you only have a few hundred or a few thousand users, if it works, it works. It's not going to be that slow. But once you get up to billions, that's where we really care, right? At that point, we want to pick the best possible algorithms and data structures so that we don't have to waste a bunch of money on computation. So typically, what we're going to care about when we're comparing algorithms is those really big n's. Suppose we're trying to do weather simulations, or we're trying to log transactions from some financial system, or we want to take video and encode it. In those cases, the number of bits that our algorithms are manipulating is huge, and so we care about that asymptotic behavior. Like that's where you're going to get the most benefit from having a better data structure algorithm. Now I'll note that algorithms which scale well, things that look like lines, they're going to just full stop have better asymptotic runtime behavior than algorithms that scale poorly, like parabolas. Now to demonstrate what I mean by this, that there's an objection you might make, like maybe the shape doesn't matter. Let's imagine we have some operation called zerpification. I haven't told you what it is. Now let's say that zerp1 is an algorithm that takes 2 n squared operations, and zerp2 takes 500n. So the point here is you might say, well, it seems like zerp2 is better actually, because this huge constant here means this could actually be faster than n squared. But what I want to note is, well, yes, you're right. For small n, this algorithm zerp, it might be faster. It takes less, for small n, this algorithm here, zerp1, may be faster. It takes less time than zerp2. But as you go to larger and larger data sets, right, my networking site becomes more popular, or I have more weather stations for simulating the weather, or I want to track 10 years of financial data instead of 1. This algorithm is going to eventually fall behind. Now it's taking forever to finish. And even once I get up to even larger numbers, this starts looking totally flat, whereas now, relatively speaking, this parabola is just climbing up to the heavens. Okay? So scaling really, really, really matters, because for big N, the thing, like these little constants up front are not going to make a big difference, not nearly as much as the actual shape. Okay? So to introduce a piece of terminology that we'll be using time and time again here, we're going to refer to the shape of a runtime function, or actually all functions, as its order of growth. And we'll formalize that in a bit. And what I want to mention is the effect is dramatic. It often tells you whether or not you can even solve a problem. So for n equals 10, it doesn't really matter if we have an algorithm that's shaped like a line, or a parabola, or a cubic, or even an exponential, or a factorial. For very small n, for a computer that's doing about 1 million operations per second, we can solve any of them. Now, when we get out to the asymptotic behavior, it really, really matters what the shape is. We can see that for 100,000 points, or an array of size 100,000 or whatever, some collection of 100,000 items, a linear time algorithm will take around less than a second under these assumptions, whereas a quadratic or parabolic algorithm might take 3 hours. Okay, that'd be pretty bad. So scaling, very important. If the only way to do something, like let's say, I don't know, cancer diagnostics with MRIs is an n-squared algorithm, then if you can move to linear or you can move to n-log n, you've made an enormous breakthrough that might make what is otherwise totally impossible able to be commonplace. Okay, so that's the argument for why scaling really matters. So let's round out what we've done so far. We've talked about basically 2 different ways of characterizing runtimes. First with simulation, and the second with modeling. Now, so far, our characterization here, while this is a nice model with a clear interpretation, it's not exactly simple. There's a whole lot of stuff here. It's difficult to compute these. It's pretty much mathematically rigorous, but we really want to try and just drive things home and make them more simple, and so we'll be doing that in the following videos.